This lecture begins our discussion of how to do conditional execution using the PIC24 instruction set. Recall that our number sequence computer in chapter 2 had an instruction called jump conditional where we place an address, and we would jump to this address if the loc input is equal to a 1. There are many different ways to accomplish conditional execution in the PIC24 instruction set. We'll begin our discussion with these two instructions. One is called bit test skip if clear, the other is called bit test skip if set. Both of these instructions test a bit in a memory location F, and you specify what bit is being tested by a 4-bit literal. This instruction, bit test skip if clear, that's what the C stands for, skips the next instruction if this particular bit is clear, that is if it's equal to a 0. This instruction will skip the next instruction if that bit is set. This is bit test skip if set. This slide illustrates example execution of the bit test skip if clear instruction. What we're going to do with this program is attempt to emulate the program that our number sequencing computer executed. Recall that our number sequencing computer had an out instruction in which we could output a digit to a dout data bus, in this case out 8 to the dout data bus. What we're going to do is we're going to emulate the dout data bus with a memory 1 byte wide memory location called out, and this two instruction sequence right here, moving a constant to W0 and then moving that value to out, is going to emulate our out 8 instruction. Also recall that we had an instruction called jump conditional that would jump to an address if our loc input was equal to a 1. We're going to emulate the loc input by the least significant bit of this memory location named loc. So the least significant bit is going to represent this input. If this least significant bit is a 1, the loc input will be a 1. If it's a 0, the loc input will be a 0. This two instruction sequence right here is going to emulate the jump conditional address instruction. Let's see how it works. We're going to use a bit test skip if clear the least significant bit of loc. This is going to skip this instruction, which is a go to if loc is a 0. Remember that if loc was a 0, this jump was not taken, so we will simply skip the next instruction, and here we will output these 3 digits, our first 3 digits to the output location out, and then we'll output our next 4 digits as well. However, if loc is a 1, then this next instruction is not skipped, which is a go-to, and we're going to end up going to this label right here, which will only output these 4 digits. So this program essentially emulates what our number sequencing computer program tried to do, and this is an illustration of the bit test skip if clear instruction. We are not going to emphasize use of these instructions. We're going to show you in later slides some more convenient instructions for doing conditional execution. Before discussing more PIC24 instructions for doing conditional execution, let's review C language conditional test. This is the equal and not equal operators for the C language. Here's the greater and greater than or equal, less than or less than or equal. We'll also discuss using the logical and logical or test, as well as logical negation. Recall that in a C conditional test, if that test returns a non-zero value, then the condition test is true. Let's discuss the difference between logical operations such as logical negation, logical and logical or versus their bitwise operations. Logical operations always treat their operands as being either 0 or non-zero, and the return result is always either 0 or 1. So let's take a look at an example. Here we have the I value that's equal to A0. This is saying the logical negation of I. Since I is non-zero, that means that it's being treated as a 1 value, and the logical negation of 1 is 0, which is false. On the other hand, the bitwise operation for I is simply going to flip every bit in here. So flipping the bit of each bit of A0 yields the value 5F. 5F is not the same as 0. These two operations return different values. So let's take a look at some examples. Here A is set equal to 5 and B is set equal to 10. So the test A less than B, this is true, so this value right here is going to return a 1. The test A is equal to B, this is false. A is not equal to B, so this result is going to be 0. The test A greater than B, A is not greater than B, the test is false, so this result is going to return 0. Finally, A not equal to B, this is a true statement, so this is going to return a 1. Here are examples of the logical operations versus their bitwise. Here we're going to do A logical AND with B. Since A is non-zero and B is non-zero, this is going to be the true result because we're saying a 1 logical AND with a 1, that's going to be a 1. In this case right here, we're going to do a bitwise log AND of A and B. If we do a bitwise of F0 ANDed with a bitwise of B, this value is actually going to return 0. Notice that these are different. Let's do this. This is the logical OR of A and B. A is non-zero, so that's a 1. B is non-zero, so that's a 1. So the result is a 1. Here we're going to do the bitwise OR of A and B. If we do a bitwise OR of F0 and 0F, it's going to return the value of FF. Finally, let's look at the logical and negation. Here, B is non-zero, so it's a 1. The logical negation of that's going to be a 0, so the result is a 0. The bitwise negation of B with the 0F is going to return an F0. Let's review an if statement format in C. We say if some condition test, open brace, some series of statements in here that form the if body, close brace. We can also have an optional else body, and to say else, open brace, some sequence of statements for the else body, close brace. This if body is executed if this condition test is equal to a 1 if it's true. This else body is executed if the condition test is 0 or false. Let's look at use of conditional test for 0 and non-zero in if statements. The statement right here, if logical negation I followed by an if body, our question is when is this if body going to be executed? Well, if I is equal to a 0, the logical negation of I is equal to of 0 is equal to a 1. So that means that this if statement right here will only be executed if I is 0. Alternatively, you could write this as if I is equal to 0, then do this. In this statement right here, we're doing if I. What does this do? Well, if I is equal to non-zero, if it's non-zero, then that means that that test right here is going to return to a 1. So this statement right here will execute if I is non-zero. Alternatively, you could write this as if I is not equal to 0, do the if body. You need to understand all of these forms as these are all commonly used in C code. Let's look at a common mistake when using a C equality test. Here we'd like this if statement right here to be executed when I is equal to 5. So we're going to use the equality operator here, equal. This will be executed only if I is equal to 5. If I is 5, this test will return a 1, which is a true value, and we will execute this statement. This is a common mistake to use the assignment operator instead of the equality operator. The assignment operator always returns the value that is being assigned. So in this case, it's going to return 5, which is non-zero, which means that's going to be a 1 or a true value as tested by this condition. So that means that this assignment statement result is always true, and we will always execute this statement regardless of what the value of I is. This is a common mistake. Make sure that you don't make it. Some C compilers will issue a warning message when you write C code that way. Let's look at the use of a logical AND and the if statement. This is a logical AND chain here. This is read as if I is true and J is true, then do this if body. What does it mean to be true? It means that if I is non-zero and J is non-zero, then do this. Note that if one of these tests is false, then we immediately know that this AND chain is false. So if this test, if this test returns false here, there's no need to even evaluate this operand right here. We will simply skip around the if body if a test evaluates false. We will only execute the if body if all tests evaluate as true, that is, that they all evaluate as non-zero. This statement right here, if A, bitwise, and J is not the same as this statement. This is doing the bitwise and of these two operands. This if body would be executed. This bitwise and operator returns a non-zero value. Let's look at the use of a logical OR operator if statement. This is using a logical OR chain here. This is saying if I is true or if J is true. What does true mean? If I is non-zero or if J is non-zero, do this if body. Note that the first true test in a logical OR chain is going to cause execution of this if body. So if I is non-zero, we will not even evaluate this test. We will go ahead and execute this if body. This statement right here is not the same as this statement right here. This is going to do the bitwise OR of these two operands, and if that is non-zero, then it will do this. This slide is going to illustrate how one way to implement a non-zero test in C. This slide is going to use the bit test skip if clear instruction, and then we'll move on to looking at clearer ways of doing this. So we have an if statement here that says that's doing a non-zero test. It's saying if K is non-zero, execute the if body. This is equivalent to saying if K is not equal to 0, do the if body. So let's take a look at our solution. Our solution is going to start out by moving K on top of itself. Why are we doing this? This seems to be a useless operation. However, it has the useful side effect of affecting the N and Z flags. What we're doing is we're testing the value of this 16-bit operand. If K is not equal to 0, then after this move instruction, the Z flag will be 0. However, if K is 0, then the Z flag will be set to a 1. So after we do this instruction, we can test the value of the Z flag and know if K was non-zero or 0. So let's look at this instruction. This is doing a bit test skip if clear SR. What is SR? SR stands for the status register, and this is testing bit number 1 in the status register. What is that bit? It turns out that bit number 1 in the status register is the Z flag. So this is going to say bit test skip if clear. Skip if clear means skip if Z is equal to 0 around here to the start of our if body. If Z is equal to 0, then that means that our K value was non-zero, and that's what we're doing over here. We'll execute the if body, and then we'll follow through and execute the rest of the code. Well, what if the Z flag was actually a 1, meaning that K was equal to 0. If K is equal to 0, we do not want to execute this if body. So bit test skip if clear, we will not skip this next instruction and we will simply go we'll execute this go to statement, which skips around the if body and goes to in if. So this code right here implements this if test. Admittedly, these two branches right here, having two different branches in this statement, can be confusing. So we will take a look at what I think is a clearer way of doing conditional tests other than using these bit test skip if clear or bit test skip if set instructions. Another way to do conditional execution in the PIC24 instruction set is to use branch instructions. These are called simple branch instructions, and they test the state of a flag and branch to a label or an address based upon that flag. This says branch on 0. This will branch to this address or label if Z flag is a 1. That is, if the operand that was tested was a 0 value. This is branch on not 0 to some address. This will branch if Z is equal to 0. That means the operand that was tested was not 0. This is a branch on carry. We'll branch to the label if the carry flag is set. This is a branch on no carry. This will branch if the carry flag is cleared. These two branches right here are test the negative flag. We'll talk about these branches in the next chapter. This is a branch always. It's like a go-to statement. It's an unconditional branch. The branch always only takes one instruction word, and it has a limited range on which it can jump to in terms of program space, while a go-to statement requires 2 program words but can jump anywhere in program memory. So let's take a look at using our branch on 0 to implement our previous example of an if statement using a non-zero test. So this is saying if I is non-zero, execute this if body. So we'll keep this, in which we test the value of I by copying it over itself and affecting the Z flag, and we'll say branch on 0 to NF. We're going to skip around this if body if I is equal to 0. If I is not 0, this branch is not taken, and we're going to execute the if body. Notice that there's only one change of control here instead of the 2 changes of control required by using the bit test skip if clear instruction. So let's take a look at a general method for implementing an if-else form. So in C, we'd write this if some condition test. If that's true, do the if body. Else, we want to execute the else body. So how are we going to implement this in a general way in PIC24 assembly language? Well, first of all, we have to test the condition. And testing the condition is going to set 1 or more status flags. At that point, we need to implement a branch. Well, we want to choose the branch such that the branch is going to be taken when the condition is false, so that we can skip around this if body and execute the else body. So whatever branch we choose, we want the branch to be taken if the condition is false. If the condition is true, then we're not going to take the branch. We're going to follow through, and we're going to execute the if body. If we have an else body, then we always need to have a branch always here after these if body statements, because we're going to want to skip around this code and go to the end of our if statement. So let's start looking at some examples. Let's look at an equality test. So here's some C code that says if K is equal to J, if they're equal to each other, then let's execute the if body. So first of all, let's write some code that's going to test this condition. The way that we're going to test this condition is that we're going to subtract J from K. When we do this, this is going to affect the Z flags. Notice that this result here is going to be written to the W reg. We do not want to modify either J or K when we do this test, so we'll write it to the working register. And the end result here is that the flags will be affected. Well, what flags are we interested in? Well, we're interested in the Z flag. If these 2 values are equal, if the condition test is true, then the Z flag will be a 1. That's the true condition. Well, what's the false condition? The false condition is going to be when Z is equal to a 0. That means that K is not equal to J. That's the false condition. So what branch do we want to use here? We want to use the condition for when we want to use the branch when the condition is false. So we want to do a branch always on not 0, so that if K is not equal to J, we'll skip around the if body. This does not have an else clause, so we'll just branch around to a label that we're going to call NF, and we would execute the rest of the code. If K was equal to J, that would mean that the Z flag would be a 1. This branch would not be taken, so we will follow through and execute the if body. Since we do not have an else statement, we do not need a branch always here, so we'll just simply have the if body statements. What if this was a not equal condition instead of an equal condition? How would this code change? The test would be done in exactly the same way. The only thing we have to do is simply change it from a not 0 condition to a 0 condition. That would be the false condition. That is, if we took this branch, it would mean that these 2 things were equal. If they're not equal, the branch would not be taken, and we would execute the if body. Now let's take a look at the greater than or equal, less than equal test. For the equality test of K equal J, we noted that we could test that only using one flag, the Z flag. However, we'll find that for these tests, for some of these tests, we will have to use a combination of the 0 and carry flags. Let's get started by considering the comparison of K greater than J. We're going to set the flags by doing the subtraction of K minus J. If this condition is true, then we'd be subtracting a smaller number from a larger number. If that happens, then that means there will be no borrow, and the carry flag will be set to a 1. Because these two values are not equal, the Z flag will be equal to a 0. At this point, we want to ask ourselves, can we consider just one of these flags, or do we have to consider both of these flags in testing this condition? We need to distinguish ourselves from this condition of k greater than or equal to j. So let's take a look now at k equal to j. If we do k equal to j and do the subtraction, there will be no borrow. So this carry flag is the same as this carry flag, so we can't use that to distinguish these two comparisons. However, the Z flag will be a 1. So this Z flag is different from that, so we're going to need to use this Z flag here to distinguish it from this equality comparison here. So for the comparison of k greater than j, we're going to need to test the condition of both carry is equal to 1 and the 0 flag equal to a 0. So now let's test the condition k greater than j or k equal to j. So we're already seeing that k is greater than j, that after we do the subtraction, we'll have the C flag equal to a 1 and the Z flag equal to a 0. For k equal to j, if we do the subtraction, then we'll have the 0 flag equal to a 1 if this is true. Because these are equal, when we do the subtraction, no borrow will occur, so that we'll get C equal to a 1. Now, combining the results of these two tests, what we see is that we have a common factor that if either of these things is true, the carry flag is a 1. The 0 flags that don't care. It's a 0 here and a 1 there. That means that for this particular test right here, k greater than j or k equal to j, the only thing we have to test is that for the carry flag equal to a 1. This means it will take less code to write this test than it would take to do this test, because this test will require testing of 2 flags. This test requires testing of only 1 flag. Let's consider this comparison, k less than j. When we do the subtraction k minus j, if this is true, then we'll be subtracting a larger number from a smaller number. If that occurs, we'll get a borrow, and the borrow will clear the carry flag. These are not equal, so we'll also get a Z flag of 0. Now at this point, we need to ask ourselves, do we need to consider anything other than the carry flag? Let's look at the condition of k equal to j. When these are equal, there will be no borrow occur, and carry will be a 1. This carry is different from that carry. We will only get a carry of 0 when we do the subtraction. If k is indeed less than j, that subtraction will produce a borrow. So that means that we can do this comparison by only testing 1 flag condition, and that's going to be testing for carry flag equal to a 0. So now let's finally consider the comparison of k less than or equal to j. And looking at these two comparisons here, we see that the flag settings are not common. That means we have to consider these separately. So we have to consider the flag condition for k less than j, which can be tested by c equals 0. We'll also have to consider the test for k equal to j, which can be tested by just looking at the 0 flag. If these two are equal and we do subtraction, the 0 flag will be a 1. So this this condition test, once we do the subtraction, is going to be tested by checking for carry flag equal to a 0 or the 0 flag equal to a 1. For these comparisons and flag results, we did the subtraction k minus j. However, what if we did the reverse subtraction of j minus k? Using similar reasonings, we can derive all of these flag conditions for the various comparisons, and what we discover is that for the k greater than j comparison, all we need to check is the carry flag equal to a 0, and for the k less than or equal to j comparison, all we need to check is the carry flag equal to 1. What this means is that depending upon the comparison we're doing, we're going to have a preferred subtraction. If we're doing either this comparison here or this comparison here, we're going to want to do k minus j, so that we only have to check 1 flag. Similarly, if we're doing this comparison here or this comparison here, we're going to want to do this subtraction, j minus k, so that we only have to check 1 flag. So let's write some PIC assembly code for this test which is if k is greater than j, execute this if body. So let's do a subtraction. Let's choose a subtraction of k minus j. That's actually going to be the non-preferred subtraction for this comparison, which is going to force us to check the values of two flags, the carry and the 0 flag. So in thinking about these branches, we have to ask ourselves, what do these branches have to be? Well, we need to have them for the false test, which is k less than or equal to j. So let's go back, and we see that the test for k less than or equal to j is going to be c equals 0 or z equal 1. So c equal 0 or our 0 flag equal to a 1. So these branches will have to be branch on no carry, carry equal to a 0, skip around the end if, don't execute the if body, or we also skip the if body if our 0 flags are 1, branch on 0 around this. The only time that we will actually execute this if body is if we have carry flag equal to a 1 and the 0 flag equal to a 0. That will cause both of these branches to not be taken, and we'll execute the if body. So this comparison test of k greater than j using the subtraction k minus j is confusing, to be frank, because we have to test two different flags. So is there a better way to do this? Well, yes. We could use the reverse subtraction, j minus k, and then this comparison of k greater than j would only be done using one flag. So this code right here is going to do the subtraction of j minus k. We need the false test for this comparison. That false test is going to be k less than or equal to j. So let's go back to our slide and find k is less than or equal to j, and we find the carry flag equal to 1 in that case. So the false case is going to be carry equal to 1, so we'll use the branch here, branch on carry, so we'll skip the if body if k is less than or equal to j, else if k is greater than j, we will execute this if body.